just because the residual was up. If you remember, we had this nice small model here. Here you see what's going on, right? So if this is so here you see the formula of the ordinary least square estimator, right? And you see, well, if beta is the true parameter and beta hat is our least square estimator, then this is the difference between them. And if we have a consistent estimator, we want that the probability limit in the limit, if we have a lot of observations, that this difference here goes to 0, right? And you see that the most important condition, the relevant condition for that is that this final part here, this plim of 1 over n, blah, 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 that this goes to 0. And this is exactly the covariance between x and b. So whenever the residuals are correlated with regressors, we have a problem with b squared. And this is why we call this, we get an extra name, right? We call this endogeneity problem. Because now we cannot just say, we move x and everything keeps constant. Now, because of this correlation with the residuals, we cannot be sure that we can really move x and nothing else changed, right? Because there's a correlation between x and b. To make it even more concrete, we have a simulation study here, where you nicely see what happens. When, for whatever reason, we have, so this is here the true model in our simulation exercise, right? And now, so the true coefficient here, the true relation between y and x is actually 1, right? But now we have an endogenous regressors. So by simulation, we know what the correlation is, so we constructed x and epsilon in the way that you can see here, this is the data of the simulation study here, that there is a slight positive correlation between regressor and residual. So exactly that what we want to rule out if we have a correctly specified model, right? So the deviation tends to be higher, the deviation u from the true model tends to be higher if x is relatively large, right? So this true epsilon is not a white noise, purely random, uncorrelated error, it's just an error, we don't know. No, now we know that it is correlated with our regressors. So when x is large, we expect that epsilon is also large. But what happens now if we just ignore that fact? So if we ignore by least square estimation that we have actually an endogenous regressor that is correlated with a residual, with a true residual. If we ignore that fact, we estimate, we just suppose that so if we wrongly assume that the regressors are endogenous, then we estimate here you see the true regression line. The one, this here is a true one, so the one with the smallest, with the lower slope here, this is the true one here. Here's beta 1, and here you see the one that is estimated with least squares. And you see that it overestimates the true parameter beta, and the intuition here in that example I think is very convincing, right? Because look, if for whatever reason x increases by 1 unit, right? If we observe this, so if this here goes up, right, then what we actually observe in the data is that y goes up by more than 1 unit then. Why? Because of the correlation between x and epsilon, if x goes up, epsilon tends also to go up. So if x goes up by 1 unit, y will go up by more than 1 unit. And this is what explains the steeper regression line if we justify these squares, right? But this is wrong, right? Because this, the more than 1 unit increase of y is not a result of the increase of x. It's a result of the correlation between x and epsilon. Okay, and that would be a misinterpretation of the partial impact of x on y. All right. So that this is a problem in economics, and endogenous regressors or neglected correlation of regressors and the residuals. This has been demonstrated here. We have here these 4 examples. We went through these 4 examples last week. So whenever you run a regression and you can show that there is a covariance between x and u, then bam, endogenous regressors. Then we know that least square estimation will give us inconsistent results. And that means least square is not feasible. We have to do something. And you see that this is here that can, so we went through these examples, dynamic regression is autocorrelated regressors, we have this nice model of errors and variables. We have here a more demanding thing here. What happens if we actually omit a variable? So if this correlation we have of the regressors with the residuals actually stems from the fact that we miss some variable that we cannot include a variable that we should include, and we have these feedback things here when we want to estimate demand functions or supply functions. In all these cases, just from the fact that we can show that the regressors are correlated with the residuals, it follows that we have an inconsistent least-square estimation. Right? That the bias we obtain does not vanish due to many observations or something. It's not a small sample problem, right? It is an asymptotic problem. Okay, so that was the point here. Here you see the variables. So these are small things you should be able to just show, right? Because it's just what you do apply as usual rules for covariances and expected values and so on. So that would be no issue here. Here's a nice example we iterate on in the second part. So look here, this is it. This is the variable bias thing, which shows you that it's not always so. Well, that's really an interesting question, whether we have a situation where we might have an interchange problem or not. So here's really something where economic intuition and economic theory come in. Right? Remember, look here. This looks like a very nice least square regression, right? So-called Mincer equation. You want to try to explain the wage of a person by its level of education and its job experience, maybe, right? Often you have a square because experience, the effect has diminishing returns. So, and now, well, why not just estimating this with these squares? The reason is that, in particular, education here might be not an exogenous variable that you just change, which is unrelated to the error. And the economics behind was that the level of education is stems from a self-selection. So people decide whether to do a master or only a bachelor or whatever they do, right? And they decide on the basis of their properties, right? So you are not selected randomly, right? You are here because you have a bachelor, because you fulfill some conditions, in order that makes you feasible to be here. You're not randomly picked from the population, right? So therefore, there isn't if you want a self-selection problem, and if you say, well, look, just by saying I have a master is not a good argument in a wage negotiation, obviously it's also something, well, are you good at your job? Are you motivated? Are you able? And this is something that which is not in here, but should be here. Now the question is, right, so if motivation, ability, whatever, has an impact on your wage, and yes, of course it has, right? Because those who are motivated, those who are able, tend to have high wages, tend to be more successful in their jobs, obviously, right? If those able, motivated people tend to be also those with a higher education, because they self-selected into education, right? Because you are motivated, you choose to be even longer at university, right? If you're not motivated or you're not able, you would be not here, right? So therefore, you have obviously a correlation here between between education and the error, because the error contains something like an omitted variable, these unobservable motivation or ability or whatever we have no data for. Right? Okay. So, if this is positively correlated, least square will overestimate the effect of education. Right? And that makes a lot of sense. Right? So, why, so if you just regress wage or some other variable measuring the success in the job market on the length of education or in the joy of education, then you assume that all the variation in the wage depends on the choice of the education. And you neglect the fact that already education is selected. Right? Okay. So here the other variables, you see the proof why something is endogenous and therefore least square is not feasible enough. It's always the same, right? You solve and then you calculate the covariance between your regressor and your error, and if it's non-zero, then you have endogenous problem. Okay, so that's the situation we were. So we are in a linear regression model, and we have endogenous regressors. So there is some covariance between regressor and errors, and now the question is, what can we do, right? And the solution is the methods of moments. This is the second estimation strategy we have, in addition to least squares, the method of moments, and in fact they are closely related, right? And look here how they are related. The idea is the following. Well, look here. These conditions here are equivalent to the least square condition, to the first order condition of the ordinary least square estimator. Right? If you go back to Econometrics 101, when you look at a simple linear regression model, and you want to minimize the sum of square residuals, you take the first derivatives, set 0, and exactly these equations here will show up. And the point here of this slide is that you can reinterpret these first order conditions of the least square estimator as so-called moment conditions, or coming from moment conditions. A moment, remember the first moment of distribution is the expected value, the second moment is the variance, and you see here, what we do is, we say, okay, what we want to have is in this model, so choose beta 1 and beta 2, the estimators, in a way such that the expected value of the resulting error is 0, and the covariance between regressor and residual is 0. So here you see, right? So if you do this, and if you now replace, and this is a general strategy of moment estimation, you have a theoretical moment condition, and this is formalized with expected value or something or so, right? Moment, theoretical moment. And then, in order to use this for estimation, you replace your expected value by the average, right? Because how do we estimate the expected value? We take the average, right? So, and this is exactly what we do. Just replace the expected value by the average, and these are nothing but the first order condition of the least square estimator. But this shows you that least square estimation is equivalent to assuming that regressors and errors are uncorrelated. This is just equivalent. Least squares is, so minimizing the sum of square residuals, I estimate that beta and so on, is equivalent, gives you exactly the same formulas as if you would start with a moment condition. And the moment condition is I have an exogenous regressor. So least squares, ordinary least squares, chooses a beta in such a way such that this condition here holds. And this explains again this fact here, look here, what we have in the simulation study. Here. If you apply least squares, ordinary least squares, then by assumption or by construction, if you want, the resulting residuals of your estimation will always be uncorrelated to your regressors. Right? And that's not by chance or because you have proven now that they're exogenous. No, it's just by construction, because least square starts with the assumption that the regressors are exogenous. It starts with the assumption that the expected value of regressor and error blah 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 multiplied is 0. This is the start of the OLS. And if so no wonder that the result of your estimation shows you, aha, here we have no correlation between errors and regressors. But that's not a proof that your assumption was right, it's just a direct consequence of your probably wrong assumption. And here we know it was a wrong assumption. Okay? This is what endogeneity makes so difficult, right? So interesting, yeah? Because, remember the last chapters when we talk about other deviations of the standard model, like the autocorrelation or heteroscedasticity, right? As long as we start with a consistent estimate, we could always more or less see in the residuals that we estimate the model with heteroscedastic errors and look at the residuals, how heteroscedastic they are, right? Because we start with a consistent estimate. But here, if we neglect this here, then ONS is an inconsistent estimate. So it doesn't help, right? So the result we get is just nonsense. It's just wrong. We can't look at this and say, now I've learned something. No, you learn from a wrong model, so don't learn. All right? Yeah.
Sorry, could you please explain again the difference between the epsilon and the residuals? Because
the epsilon is the residual.
It's a residual.
So that's a true residual.
This is not part of the construction in that case of the OS estimator then.
No, look. Look at the simulation study. So this is the true model, right? We have a x variable and we have the epsilon. This is the true model. In the simulation study, we choose this x and f in a way that they are correlated. Right? So we know we have exactly this endogeneity problem. We know we cannot just say x goes up and that's it. No, because that correlation, if this goes up, that might also go up. So, and as a consequence, we don't know, okay, this goes up and therefore this goes up. So is it just because this goes up, or is it also because that goes up? Or, right? That's the problem. So least square, however, by assumption, and this is what I just showed you, this moment condition of these squares, least square by assumption says there is no correlation. I assume that there is no correlation. And if there is no correlation, then we have exactly these first order conditions of the least square here. This means there is no correlation. Plugging in, using that theoretical moment condition, filling it with the data, you see these are exactly the first order conditions of the least square estimation. Okay? So least square estimation is equivalent with assuming I have exogenous regressors. Right? And if they're not exogenous, well, least square breaks down. Okay? So now what is the idea of the ID estimation? The ID estimation, the general idea is you have here a problem with that x because that moment condition is wrong. You start with a wrong moment condition. Why not replacing that wrong moment condition with the correct one? Right? Yeah, then okay, if it's correct. If that would be somehow right, then we could choose this and go ahead by solving for beta 1 and beta 2. So what moment conditions, what's going on here is that we just replace now that endogenous variable x, where the moment conditions do not hold, by a so-called instrumental variable set, where the moment conditions are correct. Right? So, a valid instrument is therefore a model where exactly that moment condition holds. So we replace x, the problematic regressor, by another regressor, which is okay, which is exogenous. where we can just apply these squares. However, look, at first base that looks like a strange idea, right? I have an endogenous regressor like education. This is what I'm interested in. Oh, I cannot use it because it's endogenous. Let's replace it by something else. Huh? I'm interested in the effect of education, right? And now you replace it by something else, by some instrument. What? Huh? What can I learn from this, from that? Right? Of course, exogeneity is not the only assumption we need, right? The instrument variable must, of course, be somehow related to education or to the endogenous field. Otherwise, it makes no sense, right? To just take the weather. Yeah, the weather is exogenous, fine. Yeah, but why should you replace education by the weather? What should I learn by that? Okay, obviously, there is a second important condition, the so-called relevance condition for the instrument. And that says, yeah, set is exogenous, so I can use it, but it's not just a random variable, it has to be correlated with my problematic variable. So I replace the problematic endogenous variable by a variable that is hopefully highly correlated with the endogenous one I'm actually after. Okay, and now you see the techniques, right? You see in this very simple linear regression model, there's only one regressor, and so look here, this is the exogeneity assumption we have. So set should now be exogenous. Well, if you translate that into the empirical moment condition, this is just that, right? Expectation replaced by average. And now you have first order conditions when you solve for beta 2, for example, the slope coefficient, you get this result. Right? You see, in some, not everywhere, but in some places, set the x, the problematic x, is replaced by the exogenous set term. Okay, the nice thing is now that you can show that this is actually an unbiased estimator, an unbiased and consistent estimator, simply because the regressor is now exogenous, right? So, and this so-called ID estimator of beta 2, right? This can be, put in formulas like this, right? This is just what we did here, but in a general linear regression model. And this is not so difficult to see, right? It's on this side. Here. The only thing I have to mention that I forgot last week, right? This is a critique on this slide here. Look here, that's the starting point here. We have a linear regression model, and we have some endogenous regressors, right? Only one. We have k regressors in total, and part of these k are endogenous. Maybe not all of them, right? The point here is, in order to be well defined here, right, that this matrix modification works, you have to know, or I should have write down here, that this note here, whenever a regressor is actually exogenous, so whenever you actually don't need to instrument that, right, you just take XL as its own instrument, right? So you have 10 regressors, 7 of them are endogenous. You replace 7 of them by your instruments, and the other 3 are just their own instruments, right? So this shows you well, right? Look, if for example S would be 0, though there are no endogenous regressors, then you would see that in that case W would just be S, right? Because I do not replace nothing, right? And in that case, you see, okay, if I have no endogenous regressors, then the ID estimator is just OS. If I replace omega by X, this is just the formula of these squares. See? See? If you replace omega by X, it's just the formula. You should know the formula everything is actually exogenous, then ID estimation breaks down to the square estimation, right? Of course, interesting case is that you have some endogenous variables, right? And then you see this, and here is this small thing here shows you how this shows weird, right? But look, it's really easy to derive it, right? Look, these are the moment conditions we have. Now it's not x prime u, right? Because we have endogeneity problem, we replace the x's with the exogenous w's, the instruments, right? But for these instruments, right, if we choose correct instruments, then we know they are exogenous. And therefore they are uncorrelated with the errors, right? This is the definition of exogeneity, right? And now you see, right? If you just take this here, w prime u, what is u? U is y minus x beta, right? Multiplying out, y prime y minus y prime x beta hat. So if these are the theoretical moment conditions, just saying I have exogenous instruments, right? And now you see that I can just solve easily for beta, like this. If this is 0, this is like that, and then I take the inverse and just bam. Okay? By the way, the fact that this here is actually invertible is equivalent to the fact that I have relevant instruments, right? Because look, this here is more or less the correlation between the instruments and the axis, right? You're already used to that, right? So x prime u, here this is the correlation between w and u, right? And w root x, this is more or less a correlation between w, the instrument, and x. And if this would be 0, right, then of course that would be not possible to take the inverse. But this isn't 0 because we have a valid instrument. Where is it? Later. Okay, because it's a relevant instrument. Okay, so these are the formula of the so-called simple ID estimation. And it's called simple because we just replace one regressor, one exogenous regressor by an exogenous valid instrument. Okay? That's why it's called simple. And it's really simple if you start from that equation. So the derivation of the simple ID estimator is really simple. Because the only thing you need to know is, now my regressors are all exogenous, and therefore this holds, and therefore I can derive beta. Okay? So, a few words about the use of instruments, because this is very often the problematic or demanding thing economists are confronted with in practice. In practice, of course, it's not obvious which variable you should choose as instruments. Maybe you have several alternatives. Yeah, I don't know, right? One might say, come on, it doesn't matter, because as long as the instrument is a valid instrument, then I have a consistent estimate, so asymptotically it doesn't matter which instrument you use. That's right. Okay? Yeah, asymptotically, if I have infinitely many observations, then it doesn't matter which instrument I use. But of course, in small sample, it matters a lot. Look, of course, this number here, beta 2 hat, my estimates, will look very different depending here on what I choose here for my set variable, right? Whether I use mother education or father education, in this small data example I showed you. In practice, in small samples, that will affect. So, okay, so that opens the question, if it matters which instrument I use, what are the consequences, right? Which instrument should I use then? And this is here nice to show here in the simple linear regression model. Here you see what are what are the consequences of the chosen instruments in small samples on your estimation. And here you see that, well, of course, you know, it's normally distributed, it's unbiased, yeah, everything is nice, so whatever set you use, as long as they're valid, everything is okay. But here you see, in the variance of the estimator, there it shows up. Here you see the correlation coefficient squared of set and x. And now think about it, you know, what would be a good instrument? A good instrument would be an instrument that is highly correlated with my regressor, right? If I want to replace programmatic education with some exogenous variable, the more higher the correlation, the more similar this exogenous variable is to my education variable, the better, right? If they're only weakly related, right, I replace education with something, and you know that something is, yeah, somehow related, but then no surprise, in small samples that estimator would be less reliable. And this is exactly reflected here. If you have an instrument which is not particularly relevant, in the sense that the correlation here is small, then you have a small number in the denominator and bam, variance goes up. Right? If the correlation is high, close to 1, then the inflating factor by using instruments is not so large. What you also see here is that, you know, you might say that, come on, I have your regression. Oh, I've heard from that endogeneity thing. Better I use instruments. Would that be a good strategy? What are the consequences of that strategy? You have a regression, right? And researcher A says, I have very good arguments that this is exogenous, that I don't need instruments. And there's researcher B who says, yeah, you're right, but somehow, you know, let's replace it by some instruments, just to be on the safe side. What would you say?
You probably lose efficiency of the estimator because
Exactly.
the variance of the estimate goes up.
Yeah, exactly. Yeah, you can argue with that simple formula that this is not a good idea to be on the safe side, right? If the regressor is actually exogenous and you replace it by some somehow related variable, then you lose efficiency. Then obviously the variance of your estimator goes up. Don't do it. In other words, only use IB estimation when you have good arguments to use it, when it's necessary to use it. Otherwise, you lose efficiency.
And how does the efficiency change if we have an infinite sample?
Well, this is only a small sample thing, right? So if you have infinite sample, which you never have, right? Then you have a consistent estimator, and then everything's.
So then it wouldn't matter.
Then it doesn't matter. Right? So the argument, finding good, relevant instruments, is the more important, the smaller your sample is. Right? But you know, it's always with these, you know, with these asymptotic arguments, you know, yeah, what does infinity means, right? Sometimes, you know, you can show with simulation studies that 100 observation is already large, and in some applications, you know, 1,000 observation is not large. Right? So, if we have the choice, if we think about which variable to use as an instrument in case of heterogeneity, obviously the choice matters. Right? In practice, the choice matters. So, here. So next step. Suppose we have a choice, right? In some applications, you have an exogenous variable, and you know the only instrument I have is this one. So I can't help. I have no idea. There is no data available. I have to choose this one because there's no alternative. Okay, then. Okay. But now suppose you have alternatives, and this is what actually happens in practice, right? So suppose you have L different instruments which are all valid. So they are all exogenous and they are all relevant. So they are all somehow related to your endogenous variable xk. Here, just for simplicity, we have a lot of exogenous variable and only one endogenous, like in our education example. Okay, so now what to do, right? A naive way would be, well, they're all exogenous. So what would be your suggestion to be the first step when you think about which instrument now to use? Each of these instruments gives you a different estimator, right? You plug in here in the formula, and for each of the sets you get a different estimator. So which one to use? What would be your idea?
I have no idea.
You have no idea. So if you have to choose between estimators, which one would you choose?
That would make sense.
The one with the lowest variance, okay? You have one that varies like this, and one that varies like this. I take that one. Okay? Yeah? Oh, come on.
Yeah, actually, I missed some part of it, and because
Which part?
the
Slide 148.
right now I can't give you some good answer because
Okay,
I
look.
don't say something.
Look, this shows you the result when I choose some of the sets. Okay, here's a formula that shows you the consequences of using different sets. Asymptotically, doesn't matter. In finite sample, it matters. And you see here that the higher the correlation, the better. Right? If I replace education by some instrument which is only loosely connected to education, the results are more volatile, less reliable than I would replace it with a variable that is more relevant for education. This is very intuitive. Okay, so now I have L difference here. So the first idea would be, okay, just look which of the ones is most highly correlated with my endogenous regressors. And this is the one I take. Okay? But this is not the best way you can do it. Because, and this is the idea here of the two-step least-square estimator, which leads us to the so-called generalized ID estimator. Look, what a two-step or a two-stage least-square estimator does is the following. Look, you want to replace the endogenous xk by some exogenous variable. That's all the idea of ID estimation. Replace endogenous by exogenous and apply least squares. If you replace that, choose a variable that is maximal correlated with your endogenous problem, with your endogenous variable. Right? The higher the correlation of your instrument, the more relevant it is for your endogenous variable, the better. And this is a naive strategy to do it, right? Look here, if you run this regression, the endogenous, on all these exogenous variables, these are just by assumption for simplicity, and these are because they are valid instruments, right? On the right-hand side of this regression 18 here are only exogenous regressors. And what you do now is, if you run a regression on that, and if you take the fitted values, this fitted value is obviously a linear combination of exogenous variables. So it's exogenous. Right?
The other x's are still endogenous.
No, by assumption of that model here, we assume that these are exogenous. So you can only put
Oh, so
in here
just xk
exogenous.
is sorry, just xk is exogenous.
Yeah,
Okay.
exactly. This is what you understand. Yeah, and this is just for simplicity, because you can do this, what we do here for that variable, you can do for any endogenous variable, right? So you run that regression, and what you do by running the regression is, you do exactly what we're after. You choose that combination of exogenous variables that is most closely related, most highly correlated with exogenous by construction, and it is, because it's coming from that regression here, it is the one that exploits information given by all the instruments in an optimal way. Okay? And this is now done. This is the first step of a two-stage linear d-squared. Because in the second step, we just replace the endogenous variable by that one. And that's it. So the intuition is of a two-stage d-square estimator is super clear, right? I have an endogenous variable, I replace it by some exogenous variable, which is, however, most highly correlated with one, and then I took that, replace, and run d-squares. It's a two-stage d-squared because there are two stages, and in both stages I apply d-squared. Yeah.
But isn't it now correlated to the other axis?
Yeah, and doesn't matter.
But
That was also maybe correlated. So there might be some correlation between the axes, but that doesn't matter. This is not a regression.
Oh,
Right? That's normal. Okay? So what you see is for ID estimation, the number of instruments must be greater or equal to the number of endogenous variables. So if you have 5 endogenous variables, you cannot do this for only two instruments, simply because the resulting matrix would then not be invertible anymore. Right? So the general rule is at least as many instruments as, so independent instruments as endogenous regressors. Okay, so this is the idea of the two-stage least-square estimator, and here is the formula, you know, and don't be afraid, because this here is just, you know, together with that note, right, that you replace, probably, that you replace exogenous variable by its own instrument. This is really easy to see how it works. Look, realized ID estimator. This PV matrix, PW matrix, this is a projection matrix. You know from chapter 2 or 3 or whatever when we talked about the geometry of these squares. Remember, it's just like this. This is just for recall, right? You don't need that already. It's W, W prime, W over -1, and so on. Okay, this is the projection matrix. And what does that projection matrix in the square do? If you run a regression of X on these exogenous regressors W, right? So if we do now exactly what we do here, here, the first stage, what we do is we regress X, 1, 2, 3, 4, blah, 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 on W. So we multiply this here times X. This is what we do when we run a regression of X on W. Okay? Go back to chapter 2. So, X hat is therefore, here, this here, these are the fitted value of such a regression. So I have my regressors, x1, 2, 3, 4, k. I regress them on the instruments, plenty of them maybe. Maybe there are here in W, it has to be at least k, right? If I have k regressors in X, I have to have k instruments, but there could be more, right? Like in that example here. One endogenous variable, 20 instruments, I don't know, right? So same here. I regress the axis on the instruments. The result is x hat, the fitted value, and this is just PVX, right? If you can't remember, go back to chapter 2, check. When we derive least-square estimator, exactly these formulas come. But not with W, but with X, because there we regress on X, right? So, and now look what that means. If these W's here are valid instruments, so they're exogenous and they're correlated with X, then this is a moment condition. PWX transposed, so which gives x prime PW. This here is uncorrelated to the residuals. You see, it's exactly like here. But now it's more complicated because we have more instruments. And we have this first step, right? Now we do not say, we have one instrument and that instrument is exogenous and therefore uncorrelated with the residuals. Now we say, we have lots of instruments and lots of regressors. And we regress the probably endogenous regressors on W, and the result is exogenous. This is that, this is that. This is just the moment condition. And look, well, if you multiply it out, if you solve for beta, this is exactly. I guess it's on that slide. Wait. Let's give. Here, look here. This is the moment condition. If you solve for beta, you get exactly. This is just matrix kind of problem. One line. This is the generalized ID estimator. Okay, and this is equivalent to the 2-stage least-square estimator I showed you in this easy example. Right? Understanding that formula means understanding, in the first step, I regress x on PV, results in PVX. In the second step, I use this PVX to run a regression on y on PVX. And this is exactly what's then coming out. Okay. I emphasized already last week that the point estimator of a naively done two-step, manually performed two-stage least-square estimation and that this estimator here are identical, but there's a difference with the standard deviations, right? Because this here is sigma squared. This is the variance of U, right? But the problem is, if you do it manually, these two-stage least-square estimator, so if you do it exactly like in this example, right? Here, look. Yeah. In that example, we have this probably endogenous variable. Yeah, this is a least-square regression, which might be an inconsistent estimator, right? And then we'll replace education here. This is the first. That would be the first step, first stage of our two-stage least-square estimator. Yeah. We regress the education level on the exogenous variables and our instrument. And we argue to know why mother education should be an instrument, a valid instrument for daughter's education. Yeah, because on the one side it does not fit in the weight equation. So this is an adjusted regressor which should actually be in. And it is correlated with the education of the daughter. Yeah, because mother and daughters have very often tend to have the same education level, or similar education level. Right? So and here you see the first stage. Yeah? This is exogenous, we'll replace it, then here, and this would be the ID estimator. Problem, the standard error. The standard error here, coming from this manually performed thing here, is not the correct one, because if we do it by hand, manually, run a regression, take the residuals, put residuals in the second regression, right? Then the second regression does not know that this is actually not an observed variable, but a generated regressor. Right? So, and therefore, the least square here, the standard error, is just the estimated variance of this regression. But this is not the resonant one, right? The sigma square we need is not the one of the second stage regression, it's that one. Look, sigma square is here the variance of the true residuals of our model, and not of some artificial second stage regression we use, blah, 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 blah. Yeah, but this is exactly what happens if you just do it like this. Okay, so what what's here going on the slide is now that we here with this data just play a little bit around, showing you how the results change when we change the instruments, right? So here you see the results when we use just mother education as the only instrument, and here you see what's happening when we include. This is the first stage regression for education using two instruments. So here you see the results on regressing education, on experience, blah, 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 and on that. Now, this is the first stage of the two-stage regression, and you see, it's not only mother education that is correlated with education, father education is also relevant. Okay, not so surprising actually, right? So, and you see that, well, if we include another exogenous variable that increases the overall relevance of the resulting instrument, that can only be good, right? So, and in fact, right, if we replace that, you see that the coefficient here changes again. Again, these standard errors are not interpreted. These are the wrong ones. Okay? So, estimated return education increases from this to that. That's not a general result, it's just here in the data. I don't know. Okay? Yeah. Okay, so let's summarize. We're on a linear regression model. We have some endogenous regressors. They are endogenous because they are correlated with the residuals, and therefore we run into these problems of interpretation, and therefore the least square estimator is not consistent, causes a bias. And this is a problem because then this least square estimator resulting from endogenous regressors, we cannot, there's the risk that we misinterpret the coefficient. If the regressor is exogenous, then we can do this, what we are used to. We interpret low coefficient as a partial effect. If x go up by 1 unit, then y will go up by beta 2 units. This is how we use linear regression models in economics, right? But if this experiment doesn't work, if x goes up by 1 unit, then the low coefficient, no, because then if x goes up by 1 unit, the residual also goes up by 1 unit. Because of this correlation, right? So, go back to the simulation exercise, where we see that, well, yeah, what we want to have is x goes up, nothing else. And then we know, if now x goes up, it's only because x goes up. But if you have endogenous regressors, x goes up, residuals does something weird, and we just don't know y goes up, but is it because of x, is it because of the residual, we don't know, right? Endogeneity problem. Okay. That point tells you again, big warning, yeah? The endogeneity problem is so dangerous because it's not easily detected just by the data. Those purely statisticians, if you just have the actual numbers, right, you cannot detect it. You have to think about it. You know, you have to be an economist to, I don't know whether a pure statistical guy is given the data, education, experience, would you please run regression, they don't think about homogeneity, right? They just look at the correlation and that's it. But these correlations you cannot interpret as partial effects, as economic interpretable effects of education on something because of homogeneity, right? And this problem is probably particularly visible or known to labor economists or like you. All right, here we have some examples, and you see, if you work with time series data, if you're interested in dynamic models, remember then the problem comes from the autocorrelation in the errors, right? Then what time series analysis do is, right, they adjust the model accordingly. They just, typically they just include more legs. They allow for more And these here in cross-section analysis, it's much more problematic. Yeah, to solve it. Yeah, to find instruments that are accepted to be actually exogenous. Yeah, yeah, because remember that the relevance of an instrument is easily tested, right? Because you just take your endogenous variable and look whether it's correlated or not with your potential instrument. The relevance is seen in the data, but whether your instrument is actually exogenous, this requires economic arguments. Okay, so recap. What you've learned now is the method of moments. The method of moments as a generalization, if you wish, or an alternative to the least square estimation strategy. We start with a moment condition here. Regressors are exogenous, right? Or we have to replace them by some exogenous instruments. Start with the moment conditions, replace with the empirical counterparts, solve for your estimator. That was the method of moments. And there's a third one here. So in the next section, we will generalize this method of moments. And I'm so surprised the section is called generalized method of moments, GMM, as a second most important estimation strategy device for econometrics. And finally, the third one, the third pillar, where econometrics is built on is the maximum likelihood method. Right? This is the section, what is that in? 10 hours. Okay? We will see that in some specific examples, especially in our linear regression models, all three give more or less the same results. Right? Like in the method of moments thing, where we found that the method of moments is just a reinterpretation of the squares. Right? Very similar results hold for GMM and maximum likelihood. Some of you might have heard of Bayesian methods. Right? These are becoming more and more popular, especially in the empirical macro. We are doing here frequentist methods, in the sense that we do not talk about prior distributions and ex post and a priori and all these things. This is you cannot understand Bayesian methods without knowing what frequentist is. Okay, just a footnote. All right. So let's talk a little bit about GM. But before we do that, before I forget that, I want you to do the teaching evaluation. Last chance today. Yay, here it is. So this is the QR code from this lecture, and please do it, otherwise I think you don't care at all. Right? Let me see, it's 5, 9, 10, 13, 14. 21 people are here, so let's see. As 2 years ago or so, I had a big lecture, so hundreds of students, and I said, by the way, there's a link for a teaching evaluation on Blackboard. Please do this. And although there are really hundreds of people, there are 14 people. 14 students. And that was really, if you look from outside, it really looked like, aha, all students have gone. It's just, and that was, that's a pity, because this teaching evaluation, it has an impact, right? Of course, might be a frustrating one, right? but it's also helpful for us, right? Because we can change, and how the tutorial and the Übung, all these homework stuff, for example, that's the consequence of the teaching evaluation of years ago or so. People want to have homework and bonus points, right? So we think about how to avoid that you start to do econometrics 1 week before the exam. Right? are another expensive software package we think you should buy, right? All these things, you know, are reaction of the feedback we got from teaching evaluation. So we listen. Our things. to work on the evaluation, or already you're in set up? So, let's start with GMM, the generalized method of moments. And of course, you know, as the word already suggests, you know, it's built from the method of moments. So you should remember what we just said about the method of moments. The first order conditions, which we will use to derive our estimates, are now not some least-square criteria or something. It is these are moment conditions, we assume, right? So, and here's the situation. We see we have the regression model. We have probably endogenous regressors, right? The regressive matrix is somehow well behaved, so it's nothing zero and infinity or something like that, right? And what you will learn now is that the GMM estimator we will derive, this is really a very broad concept, which actually, you know, can deal with all the problems we already had with the square estimator, with endogenous regressors, you know. And in fact, very similar to the method of moment thing we had, one can show that the GMM estimator, you know, is so that many estimators, even mathematical estimator and the square estimator, can be interpreted as a GMM estimator. Okay. That section here follows in the notation that textbooks, which is on Blackboard, right? There is also GMM, of course, in the Davis McKinnon book, which I use for most of the other sections, but I think this was just too technical for our course, right? It's still, you will still see it's pretty technical, right? The GMM thing, but I think that's okay. So, look here. Suppose you have a vector, and this is now the notation of theta. Think of theta, right? Theta 1, theta 2, theta 3, theta 4, our regression coefficients, and now it's called theta. It is a vector that contains p unknown parameters. So we have p parameters to estimate. You know, maybe there in our application it's just a regression model, so it's just beta 1, beta 2, beta 3, beta p, right? The true parameter vector is theta 0. So like beta and beta hat, right? So theta 0 is a true value, you know, and the theta is a thing we estimate, right? So we have n observations, right? And now look, like in the method of moments, the starting point is that we say, we have no clear criteria about we have no maximum likelihood function, we have no sum of square residual thing that also does not apply here. But what we have is, we have m distinct moment conditions. Very similar to the moment conditions, we start with the least square, so this regressor is uncorrelated to that residual, right? We have now a more generalized view on it. We say, we have the moment condition is, it's a moment condition, we talk about the first moment. We have probably nonlinear some function, known function however, right? That tells us, well, if I put the true parameter value inside, then in expectation this is 0. Right? So you see this is very similar to these correlation moment conditions we had, but now it's just more general. Right? So look, remember here, here moment conditions, something is 0, right? Now it's more general. It's not just multiply this with that, and this has to be 0. It's more, wow, it can be some function, right? Okay. The idea, however, how it approached now is completely standard, like we just learned from the method of moments. So you have the theoretical moment conditions, wherever they come from, right? In macro, often from theory. And you say, you know what? I replace, in order to estimate this unknown parameter vector theta 0, I replace the theoretical moment conditions by its empirical counterpart. Exactly, I did it with the least square. Right? And then I say, okay, now we try to solve for the theta hat, and this will be our GMM estimate. one generalization, and it is the moment conditions can now look very different, very general, very weird. Yeah. Something is uncorrelated with something, something is, I don't know, that could be the variance or something, whatever you want. Not just it's uncorrelated, that's it. It could be a very general condition under C+0. But the idea how the next steps now, coming from theoretical moment conditions on parameter estimates, it's exactly the way it looks like. Right? We replace theoretical moments by these observations. And observe that. So, this is easy said, but not so easy done. Right? First of all, very similar to our method of moments thing and ID thing, we need, if we have p unknown parameters, we need at least p moment conditions for them. Right? We have p unknowns and we have to have p equations, right? P conditions, otherwise it would not be determined. Right? If m is exactly p, so you have p moment conditions and p unknown parameters, what we say is that the model is exactly identified. So, well, p unknowns, p conditions, not surprising, then there is a unique solution. Okay? This is exactly what happens in the least square framework, right? We have, the empirical moment conditions coming from the heterogeneity assumption, and we have k moment conditions and k unknown betas, and we just solve, and we have a unique solution for each beta 1 hat, beta 2 hat, beta 3 hat, and so on. Okay? In that way, it's exactly that design. However, it can be that we have more m, so it has to be larger equal, so m smaller than p doesn't work. We have not enough conditions, not enough information to solve for the estimator. But what if m is larger than p? Now we have more conditions than unknowns. What might that happen? Well, probably there is no exact solution then. Although we assume we know that all these moment conditions in theory hold, right? In practice, if we plug in numbers, it can be that it doesn't work. Because we have, I don't know, 10 moment conditions, but only 5 parameters, 10 equations for 5 unknowns, blah. In general, it doesn't work. Okay? This sounds like fun, but it isn't. Right? Because the only thing we have to do now is, look, first of all, technically, it is of course a complication, right? But look, if you have moment conditions derived from theory, economic intuition, or whatever, so we have conditions, we have information about the parameters. And now you have more information than is actually required. Is that good news or bad news? I would say, okay, it makes it a little bit different, it makes things difficult, but it's always a good news when I know more about my unknown parameters than less, right? So it would be crazy to say, no, come on, I know from theory you can derive 10 moment conditions, right? But we only need 5, just throw the other 5 away. Don't use them. Because then the calculation is much more easier and we have a unique solution. Right? Just throw away information? That's not a good idea, never. Right? So the idea is now how to exploit that additional information, all the information that you have. And look, this is how it's done. Right? You have an equation, you have maybe 10 equations and 5 unknowns, and there is no unique solution, so you do not find a vector as theta hat that really numerically fulfills all the equations, but you can choose a vector that fulfills all the moment conditions as good as possible, right? So what you do is, you plug in into your moment conditions, right? And then you say, okay, equation 1, it should be 0, but it's close to 0. Equation 2, it should be 0, but it's a little bit more away from 0, and so on, right? And then you add up all these deviations, and you square them. The new thing here is now, and that's what makes GMM a GMM estimator actually, is, look, if you just ignore that, that would just be the square deviations from 0, right? Actually, it should be 0. These are the moment conditions here. It should be 0. But, come on, the data says, no, it cannot be, you have 10 conditions, you have only 5 unknown parameters to adjust in order to fulfill this. That doesn't work. So I have, this is non-zero in the data. Okay, idea, choose theta in a way that this is as small as possible for all the conditions. And this means that you do this, G transpose, G is just the length of that deviation factor. But now comes this W matrix, and this is now not instruments or something. This is, the W is for weighting matrix. The idea is now, okay, so you have 10 equations for 5 parameters, and they cannot hold all of them. I have too many information, so to say, which is good. So I want to exploit all the information. And then I have, unfortunately, not all of these conditions can be fulfilled. So I have, right? So it's not possible. So I want to make it as small as possible. Now the idea is how to do that optimally. Because think of the following. Suppose you have 10 moment conditions for your 5 unknown parameters, but they are not all equal. The following sense that 7 of them are really, really important. You know, these are ones you really believe in. If that doesn't hold, this is really a problem for the interpretation of it. And there are 3 additional ones. Yeah, they're nice to have. Yeah, that's also true, but you know, there's a lot of uncertainty, you know, and yeah, if it doesn't work, yeah, that would be pity, but it's not dramatic as the other 7 ones. So what I'm saying is, you might have m moment conditions, but they're not all equally important and useful and interesting, right? So the question is how to weight the information of these, the different information content of these different moment conditions optimally. Just throwing away 5 of them because we need only 5 and we have 10, just throw them away, that's obviously not a good idea, right? Weighting them all equally. So if this is an identity matrix, and you say, I don't know, each moment condition is the same, you know, it's of similar quality, right? I do not differentiate between these different moment conditions. They are all somehow the same, right? Same degree of importance. Then omega identity matrix would be the natural choice, but that never happens in practice. That all moment conditions you're interested in have the same information content, the same degree of reliability or whatever. There are ones which are more important than others. And this is why GMM uses the weighting matrix. Okay? And now you minimize this function here, right, with respect to theta, and this of course is something, you know, which is done numerically. Right? So sometimes there are no closed form solutions for a GMM estimator. Right? It's just, you know, this is the goal function, please minimize. Solve, enter, once. Here's the solution. Okay? So, you see that GMM, very similar to the method of moments, is, you have to specify a certain number of moment conditions, of course, right? Otherwise you have no conditions which you can use to solve for the unknown parameters. It's like all my regressors are exogenous. That would be a special case of that, right? And then in this, and now comes the GMM part, you know, we weight these different conditions optimally in order to get the best estimated power of theta. So, what is done now on the next slide is, in the first step, we just assume we know what omega is. So, the weighting matrix. We derive the GMM estimator for a given weighting matrix. And then in the next step, we ask, aha, this is how our estimator depends on the weighting matrix. Let's choose the weighting matrix optimally. Okay? And that's then the GMM estimator. Okay. So, all right. So, this is what we evaluate here. These are the moment conditions. That should be ideally 0, right? And if these moment conditions are correct, then one can show that, you know, in the limit here, this goes to 0, yeah, because the moment condition is correct, so that should be 0. It goes in distribution to a normal distribution, right? And this J0, this is just here, as you can see here, the outer product here of that of these moment conditions. Okay, this is something we do not derive, but we come back to that when we talk about the intuition of the formula. So look here. This looks weird, but it's just a tangent, right? This is just the formula, Taylor approximation first order, it's a tangent. Here we have Gn, this is the sum of our moment conditions, which should be 0, right? And here you see how you can, if this is a nonlinear function, and we said that the small g's or moment conditions can be weird nonlinear functions, if they are smooth enough, we can, however, approximate them by a linear function locally. And here you see what's going on. We say, okay, it's Gn of theta of our vector of unknown parameters. So if we are close to the true parameter value, right? So you see that we look at the tangent of G at the point here at theta 0. So if you remember Math 101, you can just plug in here f depends on x, and here f at x0, and here you see the slope coefficient, the slope of the tangent, and this is just, you can just replace it, and you see that this is just the tangent, right? So we approximate the nonlinear function g by this, because these are numbers, right? Because we evaluate it at a certain point, these are numbers. We evaluate this here at theta 0, the true parameter value. Some notation, you see that h, that comes from Hessian matrix, this is the first derivative here of the gn. So how does my goal function, the gn should be 0, then all the moment conditions are okay, right? And the h tells you how does the value of my moment condition function g changes if I change theta, right? So this is just the partial derivative. And now the first order condition to minimize that, so if you just multiply now, look, this is our goal function, the weighted deviation from the moment conditions. Gn be Gn. Yeah, this we want to minimize. So, if we do that with respect to theta, then this is just taking the derivative of a product of matrices, right? So here we have V Wgn, and here you have 2 times this because it's a square, right? Here it's a square, and we have the inner derivative here. Though, if you now use this Taylor approximation, you can show that this here is approximately that. Right? And now you solve for theta, and you get this here. Right? No surprise, I don't expect that you memorize these formulas. Right? What I just want to show you is the logic, how these monster formulas of G and M divide, and this is the logic. Right? We start with the moment conditions. We approximate the nonlinear moment conditions by first order Taylor approximation. So we linearize everything. We take first order conditions with respect to theta. You know, whatever that is, you don't have to go to this equation, right? The idea is, however, you understand why I had to minimize this and why that should be 0, because it's a minimum, right? And now I can solve here with some algebra here for this estimation. So, and now again, you know, if you now, and now we have an estimator, and now we know how the variance, so this here is just, you know, nicely multiplied with 1 over n, you know, that you can really do asymptotics, right? What you can show is that this estimator here actually converges in distribution against something normal, and it's consistent, therefore it's 0, and it has some covariance matrix, and look here at that monster. This is the covariance matrix derived from that estimator. And how to derive this is really, you know, how, you know, we did that already in more simple applications, right? The covariance of A times X is, you know, A prime covariant and so on. You know, this here is not rocket science. This is just an application of the standard rules of covariance of a matrix multiplied with the random variable, taking the covariance. Yeah.
I just have a question regarding when was this founded, I guess, because to calculate that by hand must have.
No. Yeah, of course. And this is exactly why I don't do it on the slides, right? Because it's just, you know, you multiply, and then you cancel out. So that is nothing, aha, right? What is important is that you understand what is the general strategy here, right? This is a goal function, you place it by linear approximation, you take first order conditions, and then something comes out. And what comes out is just matrix algebra, right? So it's like having a super complicated formula where you just take first derivatives, right? And then, yeah, of course I don't see that this is right, but this is what is done, okay? So I don't want to spend too much time on the derivation of that, because I don't expect from you that you can do it. If we had 2 hours time for that, it would be a PhD program. Then we would have not only 2 hours econometrics, or 4 hours econometrics, or 1 and 2 and everything, right? Then I would devise this for you. And you would see, it's boring matrix algebra. That's all. All right, so that looks frightening, right? But what you see is already that, well, what are the determinants of that matrix? Look, first of all, not surprising, it depends on the weighting matrix. So the covariance of my estimator and the variance, uncertainty, therefore also of my estimation here, right? On the diagonal of that are the variances of my estimator. Though these estimation uncertainty depends on the weighting matrix. Yeah, of course, right? Suppose I choose a very stupid weighting matrix. So those moment conditions which are highly unreliable, these are important for me. Yeah? Not surprising that those with that stupid weighting matrix, the covariance matrix is big. Right? So the idea is now how to choose the weighting matrix somehow to minimize the uncertainty in my estimation. And in that case, I exploit all the information in the data and in the moment going to do the best way. And now check here. Here, H0, what is that? H0, let's look here. It is, how does my moment condition change if I change theta? So So theta is the unknown parameter vector I'm after, right? So if Gn is this h here, if that would be very small, what does that mean? That means I have a moment condition. I choose theta equals to 2, I don't know, right? Oh, that's the value of it. Now I'm not sure, maybe it's 4. And because this derivation is very small, that would mean if I change theta from 2 to 4, the moment condition doesn't change, right? Because the derivation is small. Therefore, the moment condition is more or less always the same. Whatever I plug in for theta, the moment condition gives me always the same value. That's not good. Because I want to know what the true theta is. So what I want to have is a moment condition which is 0 or close to 0 when I'm very close to the two-parameter vector. However, when I'm far away from my vector, when I'm at the wrong numbers, then the moment condition says bam, 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 I'm not valid anymore, I'm far away from 0 or something like that. Right? If I'm at the true vector, it should be 0. If I go away from the true vector, the moment condition should react. Right? Because otherwise I don't see that something is going wrong. Aha, so this here should be large. Right? And that already shows you what are the criteria which should be used in order to weight the moment conditions. This should be large, so weight those moment conditions, gives those moment conditions a high weight, where this gives you large numbers. And with a very similar logic, right, you see here, because if this is large, inverse, it gets small. And they want to have a small variance, right? So, what you can show, not you, right? But David McKinnon and I, is that in fact the optimal choice of the weight matrix is just J0 minus 1 inverse, and remember that is just the asymptotic variance of that one. And if you plug in this formula, J0 minus 1, this is something I could ask you actually, right? Because this is just plugging in and then multiplying out. You see that this monster formula here simplifies to that one. Okay, this is the optimal weighted matrix. It's optimal because it minimizes the variances in. Okay, and what is important, and this is the major takeaway before we close the talk, is what does that mean? Or what? Okay. What you see here is that the optimal weighting matrix of GMM, what GMM does is it penalizes deviations of GM from my moment conditions from 0 less heavily in directions that have a larger variance. So if there's a large variance, a lot of uncertainty in estimating my moment conditions, right? Then I say I want to calm down, right? Yeah, that moment condition is far away from 0, but come on, it's a very uncertain moment condition. Because J0 here is the asymptotic variance of that. If J0 is large, that means that I weight it down, right? So they're less heavily penalized. So you put a stronger weight on moment conditions that are more precisely estimated. This is what you do. Right? The smaller the variance, the higher is the precision we estimate these moment conditions, and therefore we put a stronger weight on those. Last slide for today. Here, look here. The efficiency of GMN depends on the set of moment conditions, obviously. Right? The best moment condition, that is with the smallest V, with the smallest variance, are those for which this here is large. That implies that the violation of the moment condition is strong if you deviate from the true parameter value. Right? If that would be small, that would be whatever you put into theta, it doesn't change G anyway, right? So that should be sensible to deviations from the true parameter. That's one thing. And if this here is small, because then the random variation of the moments is small. Because this has to be estimated, these moment conditions, right? And if these G functions are cannot estimate with high precision, then one of the G functions you shift down a little bit. Okay? So, come on, just write in the middle. Look here, in practice, this is of course unknown, right? And what is done in practice is the following. So if you start with R, G, and M, what is done is, if you do not start with some given weighting matrix, you start with the identity matrix, you obtain an estimate, you compute this matrix for your estimate, right? And then you re-estimate it with a new weighting matrix. And then you iterate forward. Iterate again, theta, calculate this, get a new weighting matrix, as long as the estimates converge. This is how it's done, numerically, in your computer. Okay, so you see, this is all data-driven, so you don't, so if this is here data-driven we use this omega matrix, you don't tell the computer, I believe more in this than in that, but the data tells you, come on, this moment condition is just, you know, super unreliable estimated. So, or this moment condition is just, you know, it doesn't respond to changes in theta, right? So it's not very useful, not very informative. So let's use those which are really respond to wrong values and weight those higher. All right. That's summary, right? GMM is a very popular thing, but as always, it depends on assumptions. And you see the assumptions are here just that your moment conditions, which are the starting point of everything, that those are correct. Right? It's like in the least squares example. If you start with the wrong moment condition, if you wrongly assume that a regressor is exogenous, although it's not, then everything breaks down. Same here. Right? If you estimate GMM, but you start with wrong moment conditions, then GMM breaks down. So those moment conditions for MSP, so then you have really, then you need no weighting matrix because you have just those. If M is minimized deviation condition using the weighting matrix, that can be chosen iteratively, and there are also GMM standard errors which are based on these asymptotic covariance matrix. Okay, so that was probably the most demanding, technically demanding chapter, right? But still, I think it's very useful for you to think about the logic of everything. So starting with this method of moment thing in chapter 8 already, right? So moment conditions have, what is that? Why can't we have more moment conditions than exogenous variables? Yeah. And then to start from that, to think about the G and M, where there are two main differences. First, the moment conditions can be very general, G, and second, there is an optimal weighting matrix estimated that weights the moment conditions optimally with respect to the covariance of the estimate. That is most efficient estimate. All right. So now, thank you very much for your patience, and next week we can relax a little bit more because I think maximum likelihood estimation should be familiar to you. That's exactly the level I need, right? I've heard from it, that is a long time ago. Okay, so that's about maximum likelihood. Thank you.